Okay, I think we reached the quorum, so let's get started. So our last speaker of the day is William Wang, who's going to give us our last talk on folding schemes, and he's going to talk about how to do folding from hashing. So, William, looking forward to your talk.
Cool, thanks. Is the mic working, by the way?
Yes.
Yeah, okay, cool. Great, so I guess before I start, I should say that the content of this talk is based on some work that I've done with these people. Yeah, so Binny talked quite a bit about why we care about folding schemes, how we use them. So I'm sort of going to take that as given. In this talk, I kind of want to do three things. The first is I want to give a recipe for building hash-based folding schemes. And it's going to turn out to be quite simple. In fact, you guys can build your own hash-based folding schemes probably. In the second part, I want to just give sort of a toy construction. It's not quite what we're doing in the papers, but I think it should get the main points across. And in the third part of this talk, I'm going to touch on this new way that we're proving knowledge soundness in the latest hash-based folding scheme, mainly because I think it will also be useful in other contexts, like hash-based succinct arguments. Cool. Okay, let's just get started. So first, let me just quickly review the definition of a reduction. So in a reduction, it's an interactive protocol between a prover and verifier. And they both receive the instance. The prover also receives the witness. And they just talk back and forth. And at the end, typically in an interactive argument, you would have the verifier output a bit indicating whether or not the statement was in the language. In a reduction, the verifier is just going to output a new instance, and the prover is going to output a new witness. And the claim is that this new statement and witness is in a new relation. So informally, you can think of a reduction as not actually testing membership in some relation R, but rather reducing a claim about membership in R into a claim of membership in some new relation R prime. Okay. So the definitions that we care about sort of carry straightforwardly from arguments. So for completeness, if the original statement and witness were in the relation, then the new statement and witness are going to be in the new relation. And soundness is also analogous. If the old instance was not in the language, then for any cheating prover, you can think computationally bounded as well, with high probability the new instance is not going to be in the new language. Great. So, and yeah, later on, I'm also going to be talking about knowledge soundness, which is going to be a strengthening of soundness. Okay, so with this definition, it's actually pretty easy to define a folding scheme. I claim that a folding scheme for some relation R is a reduction from this product relation R times R star to R star. So what is R star? Well, I don't really care. I can define R star as whatever I'd like it to be, so long as this reduction sort of satisfies completeness and soundness. Okay, so there's some flexibility in how we choose R star. Here I've sort of just unwrapped the image of a reduction for this specific type of folding reduction, where I want to test membership in R and membership in R star. Well, I want to reduce it into a single membership claim in R star. Okay. And intuitively, why do we care about this sort of reduction? Well, you can sort of use it to sort of compress an unbounded number of membership claims in R, sort of just by repeatedly invoking this reduction over and over again. Okay. So that's some intuition about what's going on when you use folding schemes in, let's say, IBC or PCD. Okay. Great. So let's talk about the hash-based recipe. So earlier in this week, we've seen sort of this standard way to obtain a succinct argument. And there's sort of two ingredients. So for a hash-based succinct argument, we're going to start with some interactive oracle proof. So it's an interactive proof where the verifier has query access to individual symbols of the prover's messages. Okay? And then we just need some sort of vector commitment. In this case, I'm going to be using a Merkle tree. And by compiling these two things together, we get a succinct argument. Okay. And if you want to make it non-interactive, then you can also apply Fiat-Shamir. So for folding schemes and more generally reductions, it's basically the same. So let's say I want a succinct reduction. What I can do is I can define this very analogous object to an interactive oracle proof. I'm going to call it an interactive oracle reduction, where it's a reduction where the verifier also has sort of query access to the prover's messages. Okay. And basically, using the same compilation procedure, we can obtain a succinct reduction just by replacing, like whenever the prover would send a long message, the succinct reduction would instead send a Merkle commitment to the prover's messages. Okay. And then at the end, whenever the verifier wants to query some positions, the prover is just going to open the Merkle paths. Okay. And you can also just make this non-interactive with Fiat-Shamir. Great. Any questions? Okay. So in the rest of this talk, I'm going to focus basically just on interactive oracle reductions with the understanding that sort of everything that we talk about can, via this compilation process, be turned into like sort of the actual sort of non-interactive reduction that we need for a folding scheme. Yep.
Can you explain again the difference between a proof and a reduction?
Yeah, okay. So in a proof, so I've kind of drawn it here as well. In a proof, you can imagine that the verifier is just outputting a 0 or 1, whether or not the instance is in the language. In a reduction, the verifier is going to output some new x prime. And the guarantee is that, you know, if the original instance were in the language, then the new instance will be in this new language. And conversely, if the old instance were not in the old language, then with high probability, the new instance is not going to be in the new language. Okay.
Reductions.
Yeah.
Yeah, I see.
Yeah.
So reductions are generalizations of proofs.
Yeah, that's true as well. So you can imagine that like interactive oracle proof is or just like an interactive proof is a interactive reduction where the new relation is sort of the trivial language that only contains one. Okay. Great. Anything else? Right. Okay, so let me try to define an interactive oracle reduction in a bit more detail. So first of all, we're just going to imagine that the verifier has oracle access to some part of an instance now. So here I've just split the instance into two components, x and y. You can imagine that x is just some short piece of data. Y is this long string that the verifier is not actually going to fully read, but rather only have query access to. Okay, and it proceeds as I described before. The prover and verifier exchange messages. Again, the verifier is not going to fully read in the prover's messages, but instead just query specific locations. Yeah, so it can query the prover's messages as well as the instance oracle. Okay, and at the end, the verifier is just going to output this new instance. So here I'm sort of like drawing the fact that the verifier is outputting y prime, which is some new long oracle. Now, for efficiency reasons, clearly we can't expect the verifier to actually write out a new oracle. That would be too long. So you can imagine what's going on here is that the verifier is just like, you know, selecting one of the oracles that was sent by the prover, or maybe even the old instance oracle, and it sort of just selects which one that it wants to output as the new oracle for the new relation. Okay. For now, let's just think about it as one. In general, you could imagine that it can output multiple oracles. But let's just keep the definition simple for now.
Not some sort of form of composition, like the sum of them, stuff like that.
No, I mean, I imagine you could do something, something like that.
Yeah, I'm just asking the definition.
Oracle queries to oracle queries.
Well, the new verifier to its own.
Not sure what you mean, but
The new verifier, whatever, new verifier has oracle. The new verifier that will check will have its oracle queries, and then you would just have to define arithmetically how you answer.
Oh yes, yes, sure. Yeah. Yeah. Okay. So completeness is basically the same. I'm just like adding these y's here. And for soundness, we could sort of define it like this. I'm basically saying if this, well, first of all, I'm defining this like parameterized relation. Like this relation is just parameterized by x. So if the old instance is not in the language, then with high probability, the new instance is not going to be in the language. And actually, it's going to be useful to define a notion of soundness, which is where the soundness error is sort of like a function of proximity to the language. So for those of you who are familiar with, like, let's say, interactive oracle proofs of proximity, this is sort of the same thing. Basically, I'm saying if the old instance is sufficiently far from the language, and by far I'm talking about like Hamming distance. So here delta is sort of the bound on how far I'm going to think about. Then with high probability, this new instance is also going to be far from the language. Okay. And this probability in particular can be like a function of delta. Another way to think about it is that we're sort of building a reduction for some like promise problem where either the instance is in the language or it's really far from the language. Okay. Any questions? Cool. So I have some examples of IORs that it turns out that many of us have probably encountered before. So first, let me just like fix a linear code C for the rest of this talk. One type of IOR is a proximity test. So you can imagine this verifier has access to Oracle access to some purported code word of C, and it wants to test that this is actually the case. So a proximity test is, you can just think of it as an interactive Oracle reduction where the prover and verifier exchange messages, and actually it's going to be in sort of a reduction to the trivial language consisting of 1. And so if f is actually in the code, then verifier will always output 1. And if f is sufficiently far from the code, then with high probability the verifier is going to output 0. Okay, so this is one example. Another example is sort of a reduction to proximity. So let's say I have some target relation, R, that's for example R1CS. In a reduction to proximity, the prover and verifier are going to exchange messages back and forth. And at the end, the verifier is going to output a claim that some, in this case, some combination of oracles. So the verifier is outputting 1, a scalar, and 2, 2 of the prover's oracles. And the claim is that this combination of oracles is in the code. Okay, so this is an example where the verifier would be outputting 2 oracles as part of the new instance. Okay. And okay, so the reason why I've like chosen these 2 examples is actually, you can also compose IORs. So if I take this reduction to proximity, and then I compose it with a proximity test, what I actually get in the end is sort of an interactive Oracle proof. Okay. So one way that IORs are useful is that they kind of serve as these modular building blocks for constructing interactive Oracle proofs. And it turns out for folding schemes, it's going to be useful to actually look at interactive Oracle reductions as standalone objects as well. But this is just like 2 examples of IORs that we see all the time in hash-based succinct arguments. Okay?
William.
Yeah.
I think for a general definition of what the verifier should output for the oracles, for the oracle, you can think of it as like it provides a way to simulate access to the output oracle in terms of all the oracles that it has seen so far. So in this case, you don't need to output pi1, pi2. You can just output a simulation that says, if you query this oracle, it means you query pi1 and you plus alpha times the query of pi2.
Yeah, okay, so that's a good point. If your only goal is to use IORs to build IOPs, I would say I agree. It turns out that if we want to make hash-based folding schemes, it's actually going to be important that the verifier sort of forgets old oracles that it's seen in the past.
Oh yeah, totally.
Yeah,
It can forget. Like,
okay.
Yeah, the simulation doesn't have to involve everything.
Yeah, so I mean, you need some sort of mechanism that allows the simulation to say, forget these old oracles. Yeah.
And it's somewhat annoying to keep track of what are these, like how complex these composed, like it is to keep track of how you derive the new oracle from the original ones.
Yeah.
This way it's very flat. It's a direct mapping. Kind of nice.
Yeah, I'll say that I guess sort of the way that you simulate access is sort of baked into this final claim. I think there are also other ways to define it that might be more elegant for certain things. But I think for this talk, it'll be simpler to just like view the verifier as like sort of materially outputting certain oracles. Yeah. Oh, and by the way, when you actually want to compose these two things together, right, this proximity test is only expecting like one oracle as input. So yes, you would need to like simulate, like whenever the verifier queries this point, the compilation needs to sort of query both pi1 and pi2 at that corresponding point and then actually compute what this thing is. Yeah.
Which is why I think the simulation framework is sort of a better way, because you can literally say it outputs one oracle, and then you can actually compose with the proximity test.
Yeah. I would agree.
Yeah.
I would suggest to just think of the prover sending the resulting output oracle as the last one. You can check its consistency with what you wrote there, and then the test is about the last oracle. But they're all equivalent, it's just with formulations.
Yeah, it's just a matter of definitions.
Yeah.
It's certainly possible that there's like a better definition than what I'm presenting here. But this will suffice. Okay, cool. So actually using these two reductions, I'm going to first of all give like a trivial folding scheme. Okay, so recall that, you know, for a folding scheme, we want some sort of reduction of this form. Okay. Okay, so let's say we have this target relation like R1CS, and I want to verify membership in it. What I can do is I can first run this reduction to proximity, okay, and now get a claim about membership in some code. And then I can run my proximity test, okay? And then if I want to like view this as a folding scheme, what I can do is just define this R star relation to just like carry a bit, which just indicates whether or not like everything prior to that point had also been in the relation. So the new bit at the end of this reduction is going to be the conjunction of the old bit as well as the result of running this reduction to proximity and proximity test. Okay, and the reason why I say this is trivial is because sort of there's nothing interesting going on in this blue relation, right? Well, we're kind of all the work that we're doing is here, and as I said before, this actually just corresponds to an IOP for R, and in particular, once you compile it, a succinct argument for R, and so. And when people say that, you know, succinct argument implies a folding scheme, this is sort of the reason why. And really the question when it comes to hash-based folding schemes is whether we can do better. And to be more precise, what do I mean by better? Can we construct folding schemes where the prover is actually faster than this sort of trivial solution? And also, can we construct folding schemes where the verifier is actually smaller than this trivial solution? Okay, and I want to highlight that when I say smaller, it's for a good reason. I don't necessarily mean a faster verifier. I really want a verifier that's smaller when I represent it as a circuit. Because if you look at how these folding schemes end up being used in recursive proof composition, really it's like the size of the verifier when you represent it as a circuit that matters the most. Okay. Cool. So for the rest of this talk, I'm going to focus on trying to build this, this folding scheme, which is sort of non-trivial. It's going to be simpler than, again, what we have in the papers, but I think it will be good enough for this talk. Basically, the idea is that, you know, given this original relation R, we're going to first run this reduction to proximity. But instead of actually testing proximity, we're actually just going to batch the proximity claims using this running accumulator. Okay, so in particular, this R star relation is now kind of non-trivial. It's doing something interesting. It's saying, you know, is this vector G in the code? And so given these two claims, whether F is in C and G is in C, I want to batch this into a single claim that H is in the code. Okay. And the hope is that this proximity batching protocol will be better than a proximity test. Why? Intuitively, because we're not actually testing proximity. We're just reducing two claims about proximity into one claim about proximity. Yeah.
We usually lose the distance.
Soundness guarantee or distance? You mean distance, right?
Distance is in the.
Yeah. Okay.
Say like if you refer like further than some distance parameter, then the hours.
Yeah. So I guess for all of the folding schemes I'm going to talk about, there is no loss in the distance guarantee. So if like, yeah, okay, so right now I'm talking about like the completeness case. In the soundness case, if either G is delta far from the code or F is delta far from the code, then we want the guarantee of this proximity batching protocol to be that H is also going to be delta far from the code with high probability.
It's worth mentioning why distance preservation is important.
Oh, yeah, sure. You can imagine that if you didn't have a distance preserving protocol, so for example, if this guarantee was delta, and this guarantee became like delta minus epsilon, then if you kept on running this reduction, like assuming delta and epsilon are both constants, then the reduction at some point wouldn't guarantee anything meaningful, like after delta over epsilon number of steps. Delta to 2 delta or delta to delta over 2? Oh, okay. It's, you're asking if it's trivial?
If something becomes easier.
Oh, I mean, I think all of the protocols are pretty simple, as you'll see. But yeah. Okay, any other questions? Cool. So let's focus in on this very specific problem now, which is the proximity batching. So basically, I have two claims about membership in the code, and I want to reduce this into one. And so maybe the most natural thing you can think of is, well, let's have the verifier just take a random linear combination of these two vectors. Okay. So the verifier is just going to sample some scalar gamma, and it's going to output this new claim, which says that the random combination of f and g is in the code. Okay. So for completeness, clearly this is true. Actually, it's just by linearity of the code. If both f and g are code words, then any combination of them will be in the code. And for soundness, right, if either f or g is far from the code, then with high probability, a random combination will also be far from the code. And this follows from these so-called proximity gaps for codes. And we know that proximity gaps exist for any linear code. Okay.
Now you have to assume bounds on delta.
Yes. Okay. So this next thing. Yeah. In general, like we only know proximity gaps when like delta and c are chosen properly. So for the purposes of this talk, you can think of like delta as like 1/3, so like 1/3 fraction disagree, and the distance of the code being like, let's say 2/3.
For Thomas' version, when you lose half, you don't need to assume anything.
Oh,
Space.
okay.
Go from delta to delta.
Yeah. Yeah. Okay, so this is great and all. We've taken two claims about membership in the code, and we've reduced into one claim about membership in the code. But we're not actually done. And the reason why we're not done is because sort of this new output claim actually looks different from like this input claim. Why? Well, this output claim is implicitly making some sort of statement about two oracles. Even though sort of the two oracles are defined so that they only talk about one oracle, like one vector, in reality, what is the actual amount of material that the verifier needs to pass on? Well, it's actually two things. And you can imagine if you sort of repeatedly invoke this reduction over and over again, two things grows into three things, then 4, 5, 6, and this is not tenable. You want, for a folding scheme, you really want this output claim to look exactly like the input claim. Okay. You can imagine that you might also want the verifier to, instead of outputting f and g, actually compute like f plus gamma times g itself. But clearly this just is not efficient, right? Because we can't expect the verifier to actually like go through all of the elements of f and g together. So we need a new solution. Okay. Okay, and so what we're going to do is we're just going to have the prover recommit to the combination. So the prover is going to send a new oracle, which it claims is actually just equal to this combination. And now it suffices for us to sort of check consistency between what the prover sent and the actual random combination that we want to test. Okay, and the verifier is just going to do this, right, by sampling some random index. It's going to calculate what it thinks the random combination should be at that index, and it's going to output this claim. And the claim is that this new oracle that the prover sent, not only is it a code word, but actually it's one of the code words which equals alpha at its ith symbol. Okay, so it's some sort of subset of the code, constrained by this equality. Okay, and so for those of you that are, I guess, familiar with hash-based proof systems, this should feel very reminiscent of these techniques called code switching or domain shifting. I want to highlight that there's sort of something different going on here. Or not different, but just we're sort of doing code switching for a different reason. Typically, when you do code switching, you're switching to a new code. Why do you want to switch to a new code? Maybe you want a new code with, let's say, a smaller rate, or maybe some nice structure like foldability. In our case, we're actually switching to the exact same code. All the prover is doing is actually it's just recomputing this combination of code words. So we're not actually gaining any new properties. The only reason why we're code switching in the first place is really to refresh the material so that this new claim is about a single oracle rather than 2 oracles.
Aren't you moving to a subset of the code? Constraint?
Yeah, I'll get to that in a sec. Yeah, I think the other key difference here is that we're not, like in this normal code switching protocol, the prover actually needs to prove this fact to the verifier, where in this case, we're not actually proving anything, we're just outputting it as a new claim in the reduction. Okay, go ahead.
So why are you outputting as a new claim? Can't the verifier also just query H?
Because if you think about it in the soundness point of view, H might not actually be the code word, right? We want to claim that H is close to this subset of the code, but H itself might not actually be a code word. So this is it's important that we actually output the thing as a new constraint for soundness. Okay.
Sorry, actually, it's a good question. Why couldn't the verifier just check it for itself and then not output it as part of the constraint, part of the output?
Yeah, I think maybe it's a bit hard to see, but in the soundness case, sort of, the verifier is not actually claiming that H is equal to alpha at this position in the soundness case. The verifier is claiming that H is close to some code word which is equal to alpha at this position. And so you need to check that. Yeah.
Wait, so isn't a different answer to the same question potentially also, one could do that, but you'll take a hit
Yes.
in your distance.
So actually this is what we did before,
Right.
a long
So
time ago.
These are the older techniques, and it's an example of something that is simpler. If you don't care about preserving distance exactly,
Yeah.
then you could do that.
Yes.
But since we have to preserve distance for unbounded folding, then that's not an option.
Okay. Yeah, and I just want to mention that because we're not actually checking the code switch claim, because the prover is not actually proving it, we're just outputting as part of the new claim. This means that we don't need a code switchable code. So typically, code switching requires your code to satisfy certain properties. For us, we can just use whatever code we want because the claim is just being output as in the reduction. Okay. So let me just quickly analyze the completeness and soundness of this protocol. They're basically one-liners. So completeness, recall that we know that this combination is a code word, and since H is computed honestly when you have the honest prover, then clearly H is actually going to be in this subset of the code. Okay. For soundness, again, recall that we know that with high probability, this random combination is going to be far from the code. And now let me just, for the sake of this talk, assume that there's some unique code word U, which is delta close to this H. Okay, and this is the case when delta is, for example, within the unique decoding radius of the code. Okay, so I have this code word U here. And actually, I know that F plus, like this random combination is going to be delta far from the code. And in particular, it's going to be delta far from U. So, with probably delta, my random spot check is going to hit an inconsistency between U and the random combination. And when I do hit this inconsistency, then my output claim is going to be false. Okay, and we can just amplify this to like a negligible probability, or sorry, an overwhelming probability by having the verifier do like roughly order of security parameter number of queries. Okay, any questions? Cool. Okay, so let me zoom out a bit. This is sort of the protocol that we have right now. We have some target relation, this orange thing here, and then we reduce it into a proximity claim, and then we take these two proximity claims, and then via this proximity batching protocol I described just now, we're producing this output claim. Okay, but we're still not done. Why? Because this new output claim is actually, it looks different from this input claim. Okay. In particular, we're enforcing some additional constraints on the subset of the code. Okay. And so in order to actually get a full-fledged folding scheme, we're going to sort of massage these two things to be the same by sort of defining our accumulator relation, this R star thing here, to be more expressive. And in particular, it needs to be able to capture this sort of constraint. Okay. So in order to define this new accumulator relation, I need to define a few things. So first, multilinear extensions. So for any vector u, I claim there's some unique multilinear polynomial which agrees with u on the Boolean hypercube. So here int is just sort of like a way to map bits into like indices. Yeah. So basically, u hat on the Boolean hypercube agrees with the entries of u. Okay. Okay, and now I'm going to define this new constrained code. So this is a subset of code words whose multilinear extension, when you evaluate at some point x, is equal to alpha. So x and alpha basically parameterize this subset. Okay, and you can observe that like this sort of constraint that I was interested in the previous slide is actually just equivalent to a type of constrained code where I just interpret I as bits, and then I enforce that the evaluation is equal to alpha. Okay. Any questions? Okay. So using this sort of constrained code, it turns out that we can actually do a lot of interesting reductions. And I'm not going to actually go through how we do these, but it turns out that they're fairly lightweight, and they're sort of based on like standard folding techniques. But for example, given any two input claims about membership in two different constrained codes, we can always sort of reduce this into a single claim about membership in a new constrained code about the random combination of vectors. Similarly, if we have like multiple constraints, we can always reduce this into a single constraint. Okay. And basically using these things, we can sort of build this folding scheme where now the accumulator relation is expressing membership in this sort of constrained code. Okay. And our proximity batching can basically reduce these two claims into something of the same form as up here. Okay, so I'm not going to go into the details of this, but it's basically using the same ideas as the toy protocol that I described earlier. All right. So I'm going to basically spend one slide talking about warp. This is our new accumulation scheme that sort of represents the state of the art for at least hash-based folding schemes. Really, under the hood, it sort of resembles what the protocol I've described earlier. In particular, it's instantiable with any linear code, right? And actually, instead of doing proximity batching for that special sort of constrained code that I talked about before, we're doing proximity batching for an even more expressive subset of the code. And so, for example, you can think of a subset of the code as being the code words which encode a valid R1CS witness. And why might we be interested in this? Well, it basically makes this initial reduction to proximity as simple as possible. Basically, the prover just needs to encode the witness and send it to the verifier, and then they can begin like this proximity batching step. Okay, I'm not going to talk about the gory details here, but maybe I just want to highlight two things. First is that our hash-based folding scheme performs like a linear number of operations, and the verifier actually only makes lambda times log of the statement size number of random oracle queries. This sort of stems from the fact that the corresponding interactive oracle reductions verifier only makes O of lambda number of queries to the prover's oracles. So if you want something like a hash-based succinct argument with a similar profile as this, I was actually talking to Ron about it at lunch. So we think it is possible, but you would have to jump through a lot of hoops, and the constants would probably be a lot worse. Really, like the interesting thing going on here is that the IOR verifier is only making O of lambda number of queries, whereas for most proximity tests, you're going to need like some dependence on the statement size as well. Like for example, in Fry it would be like lambda times log n, or in Word it would be like lambda times log n. Okay. Okay, so that's all I'll say about.
Does it usually generalizes to CCS, or is it?
Yeah. So when I say n more, in the paper we consider some more abstract constraint system, which includes CCS. Yeah.
And more.
And more. Yeah, it turns out that the constraint system that we consider in warp can sort of express even more things than, at least efficiently, R1CS and CCS. But I'm not going to talk about it here. OK. Great. So in the final part of this talk, I want to talk about how we do knowledge soundness in warp. OK, so this is just a diagram of a generic IOR. I'm going to define knowledge soundness. And for the purposes of this talk, I'm going to assume that there's no witnesses. So the witnesses in these relations are empty. And it turns out that it's actually still interesting how we define how to define knowledge soundness. So basically, the knowledge soundness definition is as follows. For any malicious prover with high probability the following occurs. Given some y bar prime, which you can think of y bar prime as being the actual instance, which explains why the new instance is actually close to the new relation. Okay? We can extract, given the prover and y bar prime, some y bar, which explains why the old instance was actually close to the language. Okay? So recall in soundness, right? We only guarantee that sort of if the old thing was far from the language, the new thing is going to be far from the language as well. Here I'm saying if the new thing is close to the language, and moreover we know why it is close to the language because we have y bar prime here, then we can extract something which explains why the old thing is close to the language. Okay. So how does this extractor work? Well, there are two options, and we've covered them earlier this week. First, there's this straight line extraction, where the extractor will basically sort of run this. This should be p tilde here, but it's going to run the malicious prover in sort of one shot. It can't really do anything else besides observe, for example, the oracle queries that the prover makes if we're in some idealized model. But otherwise, it's not much it can do. Another approach is some sort of rewinding strategy, where the extractor can sort of run the prover, rewind it back a few steps, and then keep on running again. And in general, can sort of restore the prover to arbitrary states. So I think Pratyush talked about this at length on Monday, but there are a lot of downsides to doing rewinding. So for example, the extractors typically are less efficient. They don't actually even run in strict polynomial time. Also, rewinding is not compatible with stronger security notions like UC security, or actually when you do recursive proof composition, it's actually kind of important for provable security that you have a straight line extractor. And so you can think of straight line extraction as the gold standard for these sorts of proof systems, at least when you're working in an idealized model, like the random oracle model. Okay. So traditionally, there's basically been two strategies to doing extraction, two cases. The first case is if your code has an efficient error corrector. So for example, the classic example would be like a Reed-Solomon code. The nice thing about this is that you can actually get straight line extraction. The downside is that we actually don't know of any, at least practical linear time encodable codes that have an efficient error corrector. So if you want a linear time hash-based proof system, then sort of this does not, you will not be able to get straight line extraction. And instead, if you do not know of an efficient error corrector, and this encompasses basically all practical linear time encodable codes, the best you can hope for is some sort of rewinding extraction. Okay. So actually in Warp, what we do is something different. We basically show how to get straight line extraction even if your code does not have an efficient error corrector. And so you can think of this as sort of getting the best of both worlds. I can get straight line extraction, and I can also get like a linear time prover by virtue of the fact that I'm using a linear time encodable code. Okay, so how do we do this? Well, I'm going to focus in on this very specific step, which is sort of when you take a random combination of two vectors. So in all of these security analyses, suppose that this random combination is close to the code. Then sort of what the soundness analysis guarantees is that both of the inputs are also going to be close to the code by this proximity gap. Okay. And traditionally, at this point in time, what would your extractor do? Well, it knows that these inputs are close to the code. I'm just going to run the error corrector on them, and I know that by this guarantee, I'm going to get something meaningful. Okay? But if you don't have an error corrector, we need to work a little bit harder. So first of all, suppose that we're given the new code word, and in particular, this new code word sort of explains why this combination is close to the code. Okay? So in particular, we know that this combination will agree with this new code word at most of the positions, like all but delta. Okay? And so I'm going to identify the specific locations where they actually disagree. And it turns out that we can sort of map these disagreement locations to the inputs. And the reason why we can map them, it turns out that they're actually going to be precisely the exact same locations where the combination disagrees, is by leveraging proximity gaps with mutual correlated agreement. So this is sort of a strengthening of the standard notion of a proximity gap, which basically says, the locations where the inputs disagree are exactly the locations where the output disagrees. Okay. And once we do that, it actually turns out that we can decode these two vectors very easily because we actually know where the errors are. In particular, just by erasing them and then running some erasure correction algorithm, we can get the actual code words which agree with F and G. Okay.
So you still get the quadratic hit for these RAA codes, but this is only for the security proof, or?
Yeah, this is for the security proof.
Yeah.
In particular, straight line extraction. Yeah.
Are the parameters for the mutual correlated agreement as good as the usual proximity gaps?
Yeah, that's a good question. So first of all, I should say that we know proximity gaps with mutual correlated agreement for all codes. We know them up past the unique decoding radius. I think it's like 1.5 Johnson bound or something. I think Hadass proved this. She's in the room. For certain codes, I think Reed-Solomon codes, we have better. We know proximity gaps with better bounds than what mutual correlated agreement guarantees. My understanding is that this is not really inherent or anything. Maybe we just don't know how to prove it yet. Okay.
I mean, asking Dan Carmon, he insists that the proximity gaps paper can be
just adapted
white boxed to mutual, but nobody has checked.
But I guess the greater motivation because of this is for codes that don't have a corrector, so RA and so on.
Yeah. So the specific thing I'm thinking about is like a Reed-Solomon code where we have better things or better bounds for just proximity gap.
Yeah, but there you don't need the strategy.
Right, there you don't need it. You can just run your Reed-Solomon list decoder.
But even then, the list decoder would be more expensive in terms of asymptotics than an erasure corrector.
Oh, so incidentally, does this work in the list decoding regime in which you?
Yeah, this should still work.
No, this strategy.
Yeah, it works regardless of whether you're not in the list decoding regime or not. So long as you have mutual correlated agreement, it will work. Okay. So maybe just let me summarize the extraction strategy. Basically, there are 3 steps. First is that we actually need to leverage the new code word, which witnesses the fact that the new output is close to the code. This is not something you have to do when you have an efficient error corrector. In order to actually do this, we need to actually redefine round-by-round knowledge soundness, which is this notion of knowledge soundness that is convenient to work with, but unfortunately didn't, at least originally, capture our strategy. So we needed to redefine it. And at least in my opinion, probably this new definition is the right one. The second thing is that we needed a proximity gap with mutual correlated agreement. As we've discussed, this is known for any linear code. And the final thing is that we need an efficient erasure correction algorithm. And again, this is known for any linear code just by solving the linear system that's induced by where the erasures aren't at the locations that don't have the erasures. What's up?
How do you identify the disagreement set?
It's like the disagreement set is the exact same disagreement set as over here. And the way that you identify this disagreement set is that, well, you have the actual code word. So you just like compare. Like wherever they differ, that's part of the disagreement set.
Okay.
Yeah. Okay. Okay, and then one thing I want to highlight is that I don't actually think that the strategy is specific to hash-based folding or anything. If you look at a lot of these linear time succinct arguments, like wherever you use proximity gaps, it probably should be the case that you can apply this strategy in order to get straight line extraction. So I've sort of listed some examples here where they use codes like RAA codes or expander codes. And previously, they've only shown rewinding extraction, but I assume, this needs to be proven, of course, but I assume that you can also do something similar there. Okay. Great. Okay, so let me just conclude with some open questions. In general, for, I guess, hash-based folding schemes, one thing is that we can take these open questions that we have for succinct arguments and try to ask, is it actually easier to do with a hash-based folding scheme? So, for example, in like Warp, we were able to get like this O of lambda query complexity with like really nice constants, even though you wouldn't be able to do that with an IOP. And so similarly, I have some just like other nice properties that would be good to have. So, for example, can we do linear time folding over small fields with negligible error? And when I mean linear time, I mean like it needs to be like O of n times lambda does not count. Like I really want it to be like O of n, maybe plus some additive like poly lambda term. Okay, with negligible soundness error, of course. We don't know how to do this with succinct arguments. Okay, but maybe with folding, it's possible. Another kind of example is linear time folding with like a constant round complexity. Again, we don't know how to do this with succinct arguments. Intuitively, for folding, maybe the round complexity might depend on like the number of things we fold, but it could be independent of the actual size of the statements that we're folding.
Which part of your algorithm is not linear time?
Oh, sorry, no, our warp is linear time.
Is it?
Yeah, but it does not have a constant round complexity. There's like, it's kind of annoying. We have this annoying step in the protocol where it does like some log round sum check. Yeah.
And then arc is not linear time, but constant round.
Yeah. So I want a linear time folding scheme with constant round complexity.
Wait, look, for question number one, are
Yeah.
you thinking about folding of constrained codes or thinking of the entire R1CS, or what would make
I mean,
I
just
think
to
the
be
challenge-
like, just to have like apples to apples comparisons, I want something of the form like relation, like target relation R1CS accumulator. I want this entire reduction to be.
I think the main issue is the mapping from the R1CS to the accumulator just once, and not
Yeah,
the.
that might be true.
That's where the challenge is. That's where you
I see.
need to handle multiplications.
I see. Yeah, I mean, we would ideally sort of bake them into the accumulator relation.
But I think if you just wanted to fold in accumulators, I bet you could do it.
Maybe. Yeah. Okay. The other thing I want to sort of propose is like, we know how to do straight line extraction for like this hash-based folding scheme. I think you can also do it for a lot of these hash-based succinct arguments. Is it true that like every hash-based succinct argument actually just has straight line extraction? Or can we come up with some like interesting succinct arguments for which this new strategy does not apply? I think sort of understanding what's going on there could also be interesting. Yeah, okay, that's all I have. You can find the links to the papers I talked about here. Thanks.
Great. Yeah. Any more questions? Everything is posted there. Seriously? No questions at all?
Could you please explain why do you have lockdowns in your protocol?
Oh, I did not explain why in the slides, but essentially,
Comes from some check, right?
yeah, it comes from some check, and where is it?
Whatever you say login rounds, it means.
Yeah. So it's like one of these like things in the toolbox takes log rounds. Actually, if you don't care about linear time proving, then we can get like a constant round thing.
Can you do log star with my recent work?
Maybe. Yes. Yeah, it's like this thing. Because we want
Which
like
one?
linear
Which
this thing. Because we want linear time proving.
Oh.
Sort of we do this trick from I think Hyperplonk. But the issue is that it's like a log n round sum check.
Oh, so you batch with it.
So like Neutron Nova has this thing where they back multiple sum check. Like a zero check style claims with a single round of sum check. Not like log n rounds, you just do one round of the sum check.
And they show it's linear time.
Yeah, it's linear. Yeah.
Is it linear in like if I have t things I want to batch, is it like t times n time, or is it actually like n O of n time?
For the prover? Yeah, it's t times n time.
Well, t times n time is not good enough, basically, because like t here is going to be like lambda. So if I don't like, well, I don't like this. This is not linear time.
Notion of linear time is overloaded in there.
Yeah, I mean, I guess the reason why is because like lambda is typically greater than like log n, right? So this effectively should be considered like even more than quasi-linear.
But doesn't the sum check-based approach still have that same cost?
No, so actually, the reason why that we can get linear time is because a lot of these claims here are highly structured. In particular, like the x values are in the Boolean hypercube. So what we actually end up getting is something like O of like n plus lambda log, like something like this, which I'm happy to call linear time.
Okay, so in that case, I have to ask the standard question, which is, this stuff is supposed to be post-quantum secure.
Yeah.
So what can you say about a QROM analysis of this?
Okay, we don't have a QROM analysis.
Is there some generic result that would give a QROM analysis of this?
I think so. I think it should be fairly straightforward, actually. If you look at... Okay, this thing here. So there is some generic result that shows if you're round by round knowledge sound, then you're going to have QROM security. The issue is that we had to redefine what this is. So you need to redo that proof. I don't think anything fancy is going on there though. Like I think you can fairly straightforwardly adapt it.
Mechanical.
Yeah, I just don't want to. Yeah.
All right, great. Any other questions? In that case, let's thank Will again. Today, and tomorrow we'll see lots of applications of everything we saw during the week.